Hey everybody, in this video, we will learn quite a bit about vapor pressure, which we were introduced to in the unit about gases. We know that at a certain temperature, a liquid or a solid will exert a certain vapor pressure if it can. Now before we move on, let's talk about the densities of solids or liquids versus gases. Generally, the densities of solids and liquids are much higher than the densities of gases. For example, the density of ice is 0.93 grams per milliliter, the density of water is 1 gram per milliliter, and the density for a gas is approximately around 0.00059 grams per milliliter. Now this depends on the type of gas, but generally, the density of the gas is around that number. Or you could write the density of the gas as 0.59 grams per liter, since for gases, since the density per milliliter is so small, we tend to use grams per liter instead. At a constant temperature, doubling the pressure from 1 atm to 2 atms will decrease the volume of water by 0.0045%. So basically, doubling the pressure does not really change the volume of water or any other liquid or solid. But if you double the pressure from 1 to 2 atms for a gas, the gas will decrease its volume by about 50%. And this is because in PV equals nRT, if we double the pressure for a constant nR and T, then the volume will be halved, or 50% of the volume will be lost. Now, let's talk about the liquid-vapor equilibrium. This is the dynamic equilibrium between the liquid and gaseous state, so you could write it in terms of a reaction, such as this, where the double arrow shows equilibrium, or in other words, it can either favor the side with the gases, or the reaction could favor the side with the liquid. Now, what does it mean to be dynamic? Well, let's read these explanations to see if you could figure it out. So, when the vapor pressure exerted by the liquid is equal to the ideal vapor pressure at that certain temperature, then the rate of evaporation, or when the liquid turns into a gas, is equal to the rate of condensation, or when the gas becomes a liquid. So, overall, nothing happens, which is why when the vapor pressure of a liquid is equal to the ideal vapor pressure it wants at that temperature, then it's considered to be at equilibrium. And let me spell that out, equilibrium. So at equilibrium, the forward and backward reactions of this reaction are equal, so they cancel out and nothing happens overall. Now, what happens when the vapor pressure of the liquid is less than the ideal vapor pressure it wants? Well, if it has a vapor pressure and it's lower than what it wants, then it wants to create more pressure, and to create more pressure, you need to turn more of the liquid into the gas. And the equation PV equals nRT, albeit modified, best demonstrates this. So P equals nRT over V is basically PV equals nRT, but just modified by dividing both sides by V. And if you think about it, if the vapor pressure is less than the ideal vapor pressure, then the system will choose to create more gas molecules, or instead increase the moles of gases, and by increasing the moles of gases, the system can increase its vapor pressure until it reaches the ideal vapor pressure. So in this case, the rate of evaporation is greater than the rate of condensation, so the net result is evaporation. So since the rate at which the liquid turns into a gas is greater than the rate at which the gas turns into a liquid, then the net result is that the liquid will overall turn into gas, and that gas is added to the system, and that increases the moles of gas, which increases the pressure and kind of returns the vapor pressure back to the ideal vapor pressure. Now, what happens when the vapor pressure of the liquid is too much and it's much higher than the ideal vapor pressure? Well, if that occurs, then the system will want to remove some gas molecules in order to lower the pressure. So when this happens, the rate of evaporation is less than the rate of condensation, so the net result is condensation. Now, have you figured out why it is called a dynamic equilibrium? Well, it's called dynamic because the two processes, the forward and the backward reaction, are happening at the same time. And what determines the net process is which one of these rates are higher. So if the forward reaction is greater than the backward reaction, the net reaction will push it forward. But if it's the opposite, where the backward reaction is much larger than the forward reaction, such as over here, then the reaction will overall lean back and go backwards. So you have to think of it as a dynamic system where two things are happening, and you have to add them up to see what actually happens overall. Now let's talk about a concept called the boiling point. When the vapor pressure of a liquid is equal to the atmospheric pressure, the liquid boils, and the point at which the liquid boils is called the boiling point. So let's now talk about the difference between evaporation and boiling. Evaporation is when a liquid turns into gas under the boiling point, and evaporation occurs because of the liquid vapor equilibrium, as we just talked about. And let's just say that this is water, for example. In evaporation, we have a vapor pressure, of course, but this vapor pressure is going to be less than the atmospheric pressure. So the pressure of the atmosphere will be greater than the vapor pressure exerted by the water. But regardless, these molecules of water, especially on the surface, some of them tend to have enough energy and they end off just turning into gas regardless of the water vapor pressure, and that's why things evaporate. But this only occurs on the surface. Now, what happens during vaporization or boiling? During vaporization or boiling, liquids are still turned into gas, and this occurs at the boiling point. And what happens is that the vapor pressure will be equal to the atmospheric pressure, and because of that, the liquid will be able to overcome the pressure caused by the atmosphere and be able to float freely. So what ends up happening in boiling is that instead of it being just on the surface, boiling occurs all across the liquid. So the liquid itself, no matter where you are in the container, has enough vapor pressure to overcome the atmospheric pressure, and because of that, unlike evaporation, boiling involves the entire liquid boiling off and turning into a gas instead of just the surface evaporating. So that is the main difference between evaporation and boiling. So now that we talked about that, let's talk about what the normal boiling point is. The normal boiling point is the boiling point when the atmospheric pressure is 1 atm. Therefore, at the normal boiling point, a liquid must have a vapor pressure of 1 atm or greater to boil it off. So now let's talk about some special cases. For example, what if you were on the mountains where the atmospheric pressure was lower than 760 millimeters of mercury? For example, what if the atmospheric pressure on a certain mountain was 700 millimeters of mercury? Would you expect the water up here to have a higher boiling point or a lower boiling point? Well, since there's less atmospheric pressure to overcome, then you don't need as much vapor pressure to overcome the atmospheric pressure, and because of that, the boiling point up high, such as on the mountains, will actually be lower than the typical 100 degrees Celsius that we see at 1 atm. Now let's talk about another special case where we have a pressure cooker, which allows you to cook things in water at a higher temperature. So in a pressure cooker, you are going to have some water, and the water will have a higher boiling point than normal. So it will have maybe a boiling point of 110 degrees Celsius instead of maybe 100 degrees Celsius. So how does that work? Well, we know that in a pressure cooker, the volume will remain constant. And during this time, the water here will start boiling, and it will create, of course, a vapor pressure. But the thing is, once you boil water enough, and if you count the air that was trapped in there when you started boiling the water, then as you add more and more heat, the air trapped in here will have a higher and higher pressure, and the air in here includes both the air that was there originally and the extra water vapor that you added through boiling the water off. And this air that's inside the pressure cooker has a much higher atmospheric pressure than the normal atmospheric pressure of 1 atm. So the pressure of the air inside this cooker might be maybe, 1.2 atms instead of the typical 1 atm. And because of that, the liquid will not start to boil yet, because the liquid needs to create a vapor pressure of 1.2 atms or greater in order to boil. And since the air inside a pressure cooker is at a high temperature and is trapped with a constant volume, then it will have a very, very high pressure, and thus the water will have to reach a higher temperature in order to overcome that atmospheric pressure. And because of that, the boiling point of the water actually increases in a pressure cooker. And this lets people cook stuff in water that is at a higher temperature than the normal boiling point of 100 degrees Celsius. Now, this is also why a pressure cooker is sometimes dangerous, because since there's a really tight lid that's on top of the pressure cooker, and because there are trapped gases in here, as you increase the temperature more and more, you will have more gases, and since the temperature is going up, the pressure will also be going up. So if the pressure becomes too much for the pot to handle, the cap or the lid might pop off, and you might have a really dangerous situation if you aren't careful. So let's move on to another topic. Let's try to relate vapor pressure and temperature. So we have done this before using data, and we get these cool curves. So for example, let's take a look at butane. So as the temperature increases, as you can see, the vapor pressure will increase for these liquids as well. So as you go up, it kind of curves like that. Now, curves are great and all, but we want to mathematically describe these curves, and scientists found a way to turn these curves into lines, which is absolutely cool because we could do math with lines. And in order to do that, scientists found that if you graph the ln, or the natural log of pressure, on the y-axis and the inverse of temperature, 1 over t, on the x-axis, instead of, typically putting a t and a p here, then you will actually get a line, and that line is very cool because it can tell you a lot of things. So scientists went a little deeper, and they actually found the equation for the line. So the equation for the line was found to be ln of p is equal to negative delta H of vaporization over RT plus a constant B. Now, what do these variables mean? Well, T is temperature in Kelvin. R will be the gas constant, either 8.31 joules per mole times Kelvin if you're dealing with joules, or 8.31 times 10 to the negative 3 kilojoules per mole times Kelvin if you're dealing with kilojoules. And delta H of vaporization is in joules per mole or kilojoules per mole, depending on which one you're dealing with. And pressure can actually be anything that's related to pressure, such as ATM, bars, or even torr. So it's a cool equation, and it looks like y equals mx plus b. And if you remember from your math class, y equals mx plus b is the slope-intercept form, and it's the equation of a line. So how does this equation look like y equals mx plus b? Well, if we kind of rearrange things and pull the t out, we will get ln of p is equal to negative heat of vaporization over r times 1 over t plus b. So all I did from here to here was just change up the equation just a little bit. Now we could figure out which one's m, which one's y, which one's x, and which one's b. So the y will be the one on the y-axis. It will actually be ln of p. So ln of p will be our y, and our x will be 1 over t, so this is our x, and b will be b. And therefore, negative delta H of vaporization over R will be our m, or our slope. So from this, we figured out that the slope of the line is equal to the negative delta H vaporization over R. So this will be very useful, and I will show you why. So this line, pretend there were numbers on this line, but I didn't draw them. So this line has an equation that's written here. So ln of p is equal to negative 5190 over t plus 20.552. And in equations, especially the equations of lines, there are no units. So don't be expecting any units. And I guess in this case, you don't have to worry so much about units as you do with your numbers. Now, that doesn't mean that you could completely ignore units, because it's still important. So we know that from here, we know that the slope of the line is equal to the negative h of vaporization over r. So the slope of this line is negative 5190, because if you think about it, this t that's at the bottom is simply just 1 over t, which is our x. So this is going to be y, that's our x, and that's our b, and this is going to be our m. So our m is negative 5190, and this is equal to negative delta HVAP over R. Now, we simply have to multiply both sides by R and by negative 1, and we get that positive 5190 times 8.31 times 10 to the negative 3 will be equal to the delta H of vaporization. And doing the math, we get that the delta H of vaporization is 43.1 kilojoules per mole. And you're wondering, where did I get this unit from? Well, if you remember, 8.31 times 10 to the negative 3 is 4 kilojoules. And since we use that number, then our answer will be in kilojoules. So 43.1 kilojoules per mole will be the delta H of vaporization. And it just goes to show that through the equation of a line, you could figure out the delta H of vaporization for this graph, which is awesome. And this closely resembles the delta H vaporization for water, which is about 40.65 kilojoules per mole. So it's pretty accurate. And yeah, so now let's talk about relating 2 points, relating one temperature and one vapor pressure to another temperature and another vapor pressure. So I will call these 2 points T1, P1 and T2, P2. And what I did first is that I substituted each of these points into the equation that we talked about over here. ln P is equal to negative H vap over R times 1 over T plus B. So I simply chugged in T1 and P1 to this equation to make this. And over here, I chugged in T2 and P2. So I have two equations, and what did I do next? Well, I decided that since this was kind of a system of equations, I decided to subtract the top equation by the bottom equation, and I got ln P2 minus ln P1 is equal to negative delta H vap over R times 1 over T2 minus negative delta H vap over R times 1 over T1. And notice how when you subtract B minus B, you get 0. So the B's cancel out, and you're left with basically this right here, equation number 1. And then we go down and we simplify it, and the rules of logarithms state that when you subtract two logs with the same base, both of these have the base e, then you could divide the two numbers, and it kind of looks like that. So ln P2 minus ln P1 is equal to ln P2 over P1. This is just a rule. Now, on the other side, I simply factored out negative delta H of vap from both sides, and I was left with 1 over T2 minus 1 over T1. And this equation over here has a very special name. It's called the Clausius-Clapeyron Equation, and it lets us relate vapor pressure to temperature for two different cases, and it lets us kind of figure out a missing variable in a way. And I'll show you in the next slide how that works. So this is a question from the Chemistry Olympiad, and let's look at it. Ethanol has a normal boiling point of 78.3 degrees Celsius and a standard heat of vaporization of 38.6 kilojoules per mole. What is the vapor pressure of ethanol at 45 degrees Celsius? So, this question basically said that ethanol has a normal boiling point of 78.3 degrees Celsius. Now, what does that exactly mean? Well, it means that at 78.3 degrees Celsius, the vapor pressure of ethanol is 1 atm, and this is because at the normal boiling point, the temperature is enough to create a vapor pressure of 1 atm to overcome the atmospheric pressure of 1 atm, and this is because at the normal boiling point, it's at 1 atm for the atmospheric pressure, and all the liquid needs is to create a vapor pressure of 1 atm to overcome that. And for ethanol, apparently, it needs to be at 78.3 degrees Celsius to create a vapor pressure of 1 atm to overcome the atmospheric pressure, and that's why it's called the normal boiling point. So, 1 atm at 351.5 Kelvin, because remember, the equation that we talked about uses Kelvin and not degrees Celsius, so we gotta use Kelvin. And what's our second point? So we have our P1 and our T1. Now, what's our P2? Well, we don't know what that is. Now, what's our T2? Well, it wants the vapor pressure at 45 degrees Celsius, so this would be T2, and I had to convert it to Kelvin, of course. And all you do from there is simply use this wonderful equation down here to do the work. So plugging in P1 over here, P2 over here, T1 over here, and T2 over here, we simply do some algebra. And if you really want to do sig figs, let's go for it. So to do sig figs with especially fractions, you got to convert them into decimals first. And notice that 1 is an exact number, and this is going to be the number with the sig figs. So your answer will have 4 sig figs as shown over here. And when you subtract these two numbers, you get 0.000298, and this has 3 sig figs. Now, what about this? Well, you could simply just move it down here and simplify it with 3 sig figs, and I underlined the third digit because that has 3 sig figs. So, what about the ln P2 over 1? Well, 1 is kind of an exact number since the normal boiling point is the temperature at which the vapor pressure is exactly 1 atm. So, it's exactly 1, and I simply simplified P2 over 1 to P2 because anything divided by 1 is, well, itself. And yeah, those are 3 things that we are looking at. And let's take a look at what we do next. So the next thing we do is that we just simplify it, so we multiply these two together, and our answer will have 3 sig figs. And we have to take the inverse log because we gotta solve for P2, so we get e to the negative 1.383, and this has 3 sig figs. And when we take the anti-log, you have to remember that the number of sig figs is going to be equal to the number of decimal places. So there are 2 decimal places, so our sig figs will be 2, and our answer will have 2 sig figs. And our answer will be in ATMs because the 1 is in ATMs. And why did we use 8.31 times 10 to the negative 3? Well, because the delta H of vaporization was 38.6 kilojoules, so we gotta use the R, that is 8.31 times 10 to the negative 3, since that's for kilojoules as well. So we gotta think about the units at the same time while we are using these equations, and if you are careful, you will get the right answer. So our answer will be A. And that's all for this video. Have a nice day.